And thanks to you, Kat and Luke, for the opportunity to talk to you all today. So my background is not in the Southern Ocean, but it's on internal waves, and particularly in the tropical ocean. So I thought I'd talk today about some of the differences in the internal wave dynamics between the two regions and learn something myself about what's happening in the Southern Ocean. So first thing I had to do was go and check where the Southern Ocean starts, or where it is, and I came across this article. So where National Geographic now recognises as another ocean out to 60 degrees south latitude, and this was last year. This is at odds with my knowledge of where the Southern Ocean starts. So this is a sign in the southwest corner of Western Australia. So for the purposes of this talk, I'm going to take the definition of the Augusta Margaret River Shire Council, where the Southern Ocean starts, not the National Geographic Society. So a bit of an overview. So the main two aspects of internal waves that I look at are internal tides, and I'll explain what they are. And I wanted to ask this question about what happens to the internal tides in the Southern Ocean. What is their fate? And the second question that I'm going to look at in the second half of the talk is, are nonlinear internal waves likely to exist? And I'll define what both of these mean in a minute. So the motivation for the first question, so there's now these global maps of internal tide-induced free surface amplitude, free surface displacement. And so this is one product from Zarin 2019. And so basically what you get is the amplitude of the steric height perturbation at astronomical tidal frequency. So this is the M2 semidonal frequency. And you get nice maps like this showing hotspots throughout the tropical ocean. So I do a lot of work in the northern Australian region. South China Sea is another hotspot, Coral Sea, etc. But then when you go to the Southern Ocean in these products, there's basically not a lot going on. So I want to try and answer why in this talk. That this steric height perturbation is smaller in the Southern Ocean. And so an additional thing to add from this product, people thought you could sort of look at these beam paths, so these high energy paths of the waves, and then you could sort of do this inference where you say the wave energy decays over this distance, so you can back out what the turbulent dissipation is over that region. And I'll show why that doesn't work as well. The second question was around nonlinear internal waves. So if you basically look at satellite imagery of the tropical ocean in coastal regions and shelf regions, you often see these sort of bands like this, these dark and light bands. So this is optical data from Sentinel-2 multispectral imager taken in this part of the Australian Northwest Shelf. And if you zoom in on this region, you see these long banded features in the sea surface roughness, and these 1 to 2 kilometre crests. And so they're the surface signature of nonlinear internal waves. And in the second part of the talk, I'll discuss why they're important. So basically, are these likely to occur in the Southern Ocean? So the key concepts about internal waves that I'll talk about today, Kyle's just given a nice talk about Lee waves, which is stratified steady flow. So now I'm going to talk about stratified oscillatory flow, where the oscillation is due to the surface tidal forcing, and what kind of wave response you get there. I'll give an overview of the velocity, density, sea surface height signature of these waves, and that's important for how you interpret different observations, both in situ and satellite, remote sense observations. And another concept that's important for this talk is this, what are called phase-locked and non-phase locked internal waves, and why they occur. And a hint, it's due to eddies. And the last thing is about this nonlinear steepening process, which transfers energy from internal tides into smaller length scales that lead to mixing. So to begin with, what happens to the internal tides in the Southern Ocean? So firstly, I'll just contrast the differences between tropical regions and the polar regions. So this is temperature profiles from World Ocean Atlas, and one is around Indonesia. So this is Indonesia in March temperature. You get this large thermocline that's 200 to 400 meters deep, and it decays exponentially as you go deeper. And Southern Ocean, the temperature difference is much less, basically. And you do get these seasonal thermocline features. So that's summer and that's winter. That's the salinity. I won't talk about that. But so the quantity of interest for internal wave propagation is the buoyancy frequency, which is basically a measure of the vertical density profile. And so if you look at the tropical ocean or the low latitude ocean versus the Southern Ocean, the thermocline strength or the pycnocline strength is about 5 times larger. It's also a lot thicker, and yeah, but as you move down deeper, they do become roughly equivalent. And so what happens then when you force an oscillatory flow over 2-dimensional topography, what kind of response you get? So this is a barotropic tide moving back and forth at twice per day. You have a small Gaussian hill, and this is 2,000 meter deep water. It's about 200 meter high Gaussian hill. It's about 10 kilometer length scale. And what you see showing velocity field here is energy radiating vertically away from the topography along these beam paths, and that energy is propagating horizontally as well. And you can see when it reaches the thermocline or the pycnocline, so this high buoyancy frequency region, which is these close together isopycnals, the energy bends, and that's due to internal wave dispersion relationship, which I won't talk about too much. But then this is showing what happens in the tropical ocean. So the bottom stratification is more or less the same in the simulations. The main difference now is the propagation of this energy along these ray paths, these beam paths. So because it's more stratified, you get the beam energy tends to flatten out. And the other thing to note here is that the energy moves away faster horizontally because it's more stratified. So you can't actually go and measure a 2-dimensional picture of the ocean very easily. So what they actually measure with the altimeter is the sea surface height perturbation from this sort of process. So it measures the sea surface height, and then you do all sorts of filtering to remove eddies and tides and whatnot, atmospheric effects, and you get left with this steric height signal. So it's the vertical integral of this perturbation density about some background mean, normalized by that background mean. So as this energy propagates away, there's small perturbations to the to the density layers, and the satellite is measuring the vertical integral of that process. But the other issue with the satellite is it only orbits every 5 or so days. So what you have to do, so now what I'm looking at is a XT plot, so showing the sea surface height, so this quantity, moving away from the topography through time. And so if you look at a single point in space, which is this red line, if you're able to resolve everything, you would get something like that. But what the satellite has to do, because it's measuring every 5 days, they do a harmonic fit. So they fit sinusoids at fixed frequencies, which relate to the astronomical tides. And they're really getting the amplitudes, these amplitudes from the signal. And so the satellite doesn't measure everything. It only measures what is explained by this term here, and that's what is called the phase-locked signal. And the residual, which is quite small in this case because it's an idealized run, is a non-phase-locked signal. And basically I'm going to show that the differences between the Southern Ocean and the poles, or in the tropics, is due to how much of the signal is phase-locked versus non-phase-locked. So, and then this was a comparison between the Southern Ocean case and the low latitude case, and it was basically showing that with the same forcing and the same bottom topography, you more or less get the same amplitude sea surface height response. So the vertical stratification in the upper ocean isn't really having a big part in that response. Another reason there could be a discrepancy is that the actual generation process of the waves is different between the different regions. So the topographic generation is a function of the tidal forcing, the topographic shape, and the bottom stratification. And there's internal tide generation theory starting with Bell, and this is an image from Kelly Waterhouse Savage 2020, where they've done this with the latest bottom stratification, latest bottom topography to update that map. So I guess the take home from this is there are hotspots of generation in the Southern Ocean. So it doesn't really explain why there are differences in that sea surface height response. Then you could say maybe it's just the way they process the data in that Zarin paper. There's a new product from a European group from Ubelman and Co. It was published this year, and this group makes more of an effort to separate the eddy signals. And you can see there's even less signal in this region, in that product. Interesting in this product, though, is there are some coastal internal tides or shelf internal tides in this region. So that's the satellite picture, and like I said, it's going over every 5 days, so it's not really telling you what's actually happening inside of the ocean. So to look at that, what I've done is gone to the IMOS, Australian Ocean Data Network, and pulled out 2 deep water moorings and velocity time series from 2 sites. So one's Indonesian through flow, current meter at 1,200 meters deep, and just plotted 15 months of data and showing the total velocity in blue and the subtidal velocity, so any sort of mesoscale flow in orange here, and then put out an equivalent water depth, so from the Southern Ocean site. so 1,200 meters deep. So both of these are below the thermoclines in both ocean basins. And so this is 12 months of data up to May of this year, actually. And you're seeing, again, the mesoscale activity overlaid on the total velocity from here. And to get a better look at that, look at the power spectra from the two velocity signals to contrast them. So the first is a low latitude site. So you have the internal waves basically occupy from F outwards, or F and higher. And the internal waves are around these, internal tides, sorry, are around these once per day, twice per day frequencies. So this is the semi-diurnal component, this is diurnal. And yeah, so what you see here is there's high energy in the mesoscale band. So that was the subtidal orange line I showed before. And you get these distinct peaks at all of the major astronomical forcing frequencies. So the lunar and solar semi-diurnal and diurnal components. So you can see individual peaks here. There's no real peak at F in this time series. In contrast, this is the SOTS, Southern Ocean data. And so the standout feature at the Southern Ocean site is these what are called spectral cusps, or these sort of widening of the spectra around the semi-diurnal frequency and the Coriolis frequency F. And another thing is the M2 and S2 frequencies are not separated in this signal, so they've sort of been blurred together. And the last thing is that these diurnal bands are less energetic again, and it's important to note that internal tides or internal waves can't freely propagate at frequencies lower than F. So the diurnal bands are mainly due to the surface tides, or the barotropic tides at the site. So first thing, why do you get these sharp peaks at the astronomical frequencies in the tropical ocean? So if you do that equivalent harmonic fit to this time series, so you just fit cosines and sines at those astronomical frequencies, you get this phase lock signal. So that's the orange. So that's all of the signal that can be explained by this harmonic fitting. And so in these low latitude regions, 73%, or at this site, 73% of the variance is explained. And also of note to note is that phase lock signal is what is actually detectable by satellite. Southern Ocean site, only 7% of the variance is explained by doing this harmonic fitting. And so the rest of that signal is basically invisible to a satellite or the altimeters. So, and to give you a broader picture of this predictability of internal tides, this is work from 2021 where we did a 12-month numerical model of this Indo-Australian basin, and it has tides and eddies and everything else in it. And then we do this harmonic fit to the sea surface height everywhere, to the baroclinic sea surface height everywhere. And this quantity is the percentage of variance explained by that harmonic fitting. And so basically throughout the whole tropical regions, it's greater than 50%. So basically the internal tides are largely predictable in the low latitudes. So even though the signal's not predictable in the Southern Ocean, we'd still like to characterize what this non-phase locked signal is caused by. And so, or how you characterize that non-phase locked signal, I should say. And so the way you characterize it is the more non-phase locked it is, the greater the width in spectral space, or the spectral cut width is. And I'll use some idealized simulations to try and explain why that occurs. So these are idealized simulations from Pont and Klein 2015. And so they basically start out with this baroclinically unstable frontal region. So think of the Southern Ocean, I guess. These are distances in kilometres. And what they do is have an internal tide source region in the south, and they propagate the waves through this eddying field. And then they analyse the data by fitting a mean component and these cosine and sine components to small 2-day windows of that data. And what they're looking for, so with a phase lock internal tide, the map of this term here, which I'm showing over here, should stay constant. Whereas in a non-phase locked internal tide field, it'll move around in space and time. So playing that forward now. So what you're seeing here is that the source region, and as they hit that eddy field, they basically become non-phase locked and moving around in time. So the eddy field's chaotic, and that's making the internal wave field somewhat chaotic. So the way to characterize that level of chaoticness, I guess, is looking at the autocovariance of the tidal velocity at different points. So what I've done here is taken the tides or the velocity from this point, the black, and this other point, orange. And that's what I'm showing here. So this is the total velocity signal from the black here. So you can see it's sort of constant and then wobbles around a little bit. And the orange, it's wobbling around a lot. So if you look at the autocovariance of those two signals, so this is autocovariance here and this is time lag on this axis, you can see that at the black site, it stays constant for longer, and in the eddy field, it decays away much quicker. So what we can do is parameterize that autocovariance into this parametric expression, which has this, so it's a Gaussian multiplied by a cosine. So cosine is giving you this part, so that's the forcing frequency. And this lambda t term is giving you this rate of decay of this this Gaussian, and you can call that a decorrelation timescale. And so, yeah, so just fitting those 2 points, you can get the inverse timescale here is 8 days when you're in the eddy field and 40 days when you're not in the eddy field at these 2 points at least. But what you can do with that as well is you can get the power spectral function by plugging this expression into here, and then you get a a function for the power spectral shape. So that's what I'm showing here. So basically you have this Gaussian term again, and so that lambda t is setting the width of that Gaussian. So this is the power spectra of those 2 points in the solid, and then the dashed are the parametric fits. So, and then, yeah, so lambda t is this quantity that we care about that's setting this spectral width. So in that Pons and Klein paper, they look at different levels of energy, and so this is their most energetic case where you have very turbulent field here. And then this is the internal tide response. Looking at the autocovariance function at that orange point, you can now see that time scale is much shorter again. So it was 8 days, it's now 3 days. And then the spectral width is now wider again. So I guess the point of all that was you can use that information to try and interpret what is going on in this Southern Ocean site. So basically the waves are going through an eddy field and they're causing that spectral broadening to occur. And so, yeah, I guess in that Pons and Klein paper as well, they show that this decorrelation timescale is actually a function of the mesoscale turbulence. So they increase the eddy kinetic energy in these runs, and they show that decorrelation timescale basically decreases. So although the internal waves aren't predictable using harmonics, you can characterize them somewhat using this decorrelation timescale. So I guess to answer that question, what happens to the internal waves, internal tides in the Southern Ocean? I think they just go through an eddy and they become decoupled from the tidal forcing, and they're basically undetectable from satellites. So now I'll change gears again and I'll look at nonlinear internal waves and are they likely to exist? So going back to the low latitudes, you can, so before I showed an optical image, but there is this Sentinel-1 satellite which has synthetic aperture radar on it, and you can go to this website and browse these images. But basically the SAR, synthetic aperture radar, or SAR, can see through clouds, so you can potentially see these wave signatures like this one in Lombok Strait in any region. So I guess around Antarctica there's a lot of clouds, so it's a better tool for looking in that region. And this was another example. So this is a region where we do a lot of work, field work at UWA, and this is another example of what you see at the surface. So I guess why nonlinear internal waves matter. So they're a mechanism that transfers energy from the internal tides down into 3D turbulence. And so if you take measurements on the continental shelf in Northern Australia, basically all the mixing is dominated by these breaking nonlinear internal waves like this one here. So this is showing a core of cold water coming onto the shelf, and you're seeing overturning in the back of the wave here. So this is what we call breaking mode 1 wave of elevation. And this is in 120 meters of water. It's not 40 meters water depth, but we're just measuring the bottom 30 meters. This is another example where it's a mode 2 wave. So mode 2 is where the isopycnals separate around the around the thermocline. So you can see ice picnicals going down here, going up here. These wiggly bits are what we're saying is wave breaking in that core. And basically why this is interesting is it's a mechanism where mixing can occur away from the boundary and in the thermocline in this case. So you don't need bottom topography to induce this kind of wave breaking. Another reason is transport of material near the bed in both sloping and flat regions. So like I said, you don't need sloping topography to get these nonlinear internal waves occurring. So these are observations from a PhD student, Will Edge. And so we're showing 2.5 hour time series of water temperature and 250 meters of water. So this is a mode 1 nonlinear internal wave signature. This is about half an hour this time here. You get this burst in bottom velocity. And in the lee of this wave, we're looking at suspended sediment, which has been derived from acoustic instruments and calibrated acoustic instruments. So what you see is after this burst of strong velocity, you get this ejection of material away from the bed and up into the water column. And this is another example from Will's PhD where it's now on a sloping bed. And so this is different dynamics. So this is a breaking wave moving up the shelf. So this core of sediment is actually moving with the wave core, whereas in this case, it's actually ejected by the wave moving over. Yeah, so anything to do with transport of materials or mixing of materials away from the bed, these waves are important. So to start looking at why nonlinear internal waves occur in the tropics relatively commonly, we can look at weakly nonlinear theory, so KdV equation in this case. So basically, you're modeling the time rate of change of a surface, so an internal surface, given by its propagation, linear propagation. This term's nonlinear steepening, and this is a dispersion term. So you have these three parameters, C, alpha, and beta, and they're all functions of the buoyancy frequency squared and the vertical profile of it, as well as the depth of the water column. And just one caveat, there's no rotation in this model. But so if you plug in some tropical buoyancy frequency profile and you force an internal tide at this offshore boundary, so it's a 12.4 hour sinusoid with a wavelength of about 50 kilometers, you can see after about 100 kilometers that the wave starts to steepen and you form these wave trains. So this is the nonlinear waves that we're interested in. And this is a numerical simulation, so put a sponge here. This is the same amplitude boundary condition, but now with Southern Ocean stratification, propagating over 300 kilometers, and nothing happens. So then the question, why doesn't anything happen in the Southern Ocean case? So it's to do with this nonlinear steepening process, and in particular this alpha parameter, which governs this nonlinear steepening rate. So if you plug a sinusoid into this and you assume that the time rate of change of this amplitude is in balance with this nonlinear steepening rate, you can come up with an expression for a steepening length scale or a growth length scale. So that's it's inverse of alpha, K, which is a horizontal wave number of your initial condition, an A naught, so the amplitude of your initial condition, or you can rearrange that into the linear phase speed and the frequency. So assuming K equals omega on C, you can get this expression. And you can also think of it in terms of the length scale. So how long you need, how big your domain needs to be for this wave to steepen. So you multiply this by C again. And so just looking at these numbers for the two regions, so this alpha, the inverse of alpha in the low latitude is 75 seconds, and this steepening length scale is 128 kilometers, given the boundary condition here. And you can see this 128 kilometers roughly corresponds to this region here, where the wave starts to steepen and become nonlinear. In the Southern Ocean, inverse of alpha is much larger, and then this steepening length scale is now at least an order of magnitude larger. So basically the waves, given the differences in stratification, they require much more distance to steepen. And so we can say they're less likely to form given the stratification. And I haven't even talked about rotation, and I'm not going to, but that's another influence. But if you go to a bigger domain, so this is now, 3,000 kilometers instead of 300 kilometers, you do see eventually that these waves start to steepen around this 1,200 kilometer mark. So given enough time, I guess they could occur. And I mean, the other thing that could enhance this steepening process is the interaction with the mean flow. And there is some evidence of this steepening in these hydrostatic 3D simulations, where you see these sharpened fronts occurring in the wave field. So there's potentially like local scale opportunity for these types of features to form in those eddy fields. So I went back and looked at this Sentinel-1 data and just looked around some topographic region where I thought there might be some sort of nonlinear internal wave signal. So this is an island off the Antarctic Peninsula here. And so we're at 60 south or 59 south. And you get these, what I think are lee waves. So I guess the flow is going this way. And you get these wakes occurring where the wavelengths here are about 5 kilometers. So I think they're too long to be any sort of surface wave signature, but I could be wrong. This was another example where, again, you're seeing these lee waves forming behind these islands. In this case, you see this sort of what I've called a dipole eddy, where you get water going in this way and this way, which could also be topographically influenced as well. So yeah, I guess finish up there. So the key points that I want to talk about. So there, in the global maps of internal waves, it's probably the non-phase locked signal that's not being picked up by the satellite, which is leading to these sort of low spots in internal tides in the Southern Ocean. And it's probably not the turbulent dissipation of internal waves propagating through the medium. This decorrelation timescale is probably the parameter of interest, and I don't think anyone has quantified that globally from the models, so it's definitely worth looking at. In terms of nonlinear internal wave formation, it's the sharp stratification and all large forcing that is required for these waves to form and steepen quickly. And I guess in terms of multi-scale interactions, this nonlinear steepening process directly transfers energy from internal tide scales down to mixing scales without any other interactions, so without wave-wave interactions or anything like that. So it's an interesting process. Like I said at the start, this was all relatively preliminary work for me. So there's some GitHub code and some links in there to these different data sets. So go in there and be free. Thanks.